Picture a family at the beach. It is approximately 2 in the afternoon, which any dermatologist will tell you is essentially the sun's peak aggression window. The father has applied sunscreen once at 9 in the morning before they left the house and considers himself protected. The kids have been in and out of the water 17 times, and their sunscreen coverage is now distributed roughly equally between their skin, the ocean, and a passing pelican. By 6 o'clock, the assessment will be grim. Shoulders glowing red, noses that look like someone held a heat gun to them, the backs of knees, always the backs of knees, the body's most reliably forgotten surface, radiating a warmth that will make sleeping a logistical challenge for the next 3 nights. The youngest child will spend tomorrow wearing a shirt in the pool and explaining to other kids that it hurts to move her arms in a way that radiates from her entire chest area. 20 meters down the beach, a pelican lands on a post and sits there. The full force of that same 2 o'clock sun is hitting it directly. It has been outside all day, every day, its entire life. It has applied no sunscreen. It will develop no sunburn. Tomorrow it will be fine. It will look, in fact, exactly the same as it always does, because the sun that is quietly cooking several members of this human family is doing essentially nothing to the pelican. And it is not just pelicans. The lion sleeping on exposed rock in the Serengeti at noon. The seal hauled out on a sun-blasted rocky coastline for hours at a stretch. The iguana basking directly on equatorial rock, specifically to absorb maximum solar radiation as a thermoregulatory strategy. The horse standing in a field all day, every day. Every wild animal on the planet is spending significantly more unprotected time in direct sunlight than any human, and essentially none of them come home with sunburn. Start with what sunburn actually is at the cellular and molecular level, because understanding the mechanism makes everything else in this story considerably clearer. Sunlight contains radiation across a spectrum of wavelengths. Visible light, the portion of the spectrum human eyes detect, is sandwiched between infrared radiation at longer wavelengths and ultraviolet radiation at shorter wavelengths. Ultraviolet radiation comes in 3 categories: UVA, UVB, and UVC. UVC is almost entirely absorbed by the atmosphere and is not a significant factor at the Earth's surface. UVA penetrates deeply into skin tissue, but causes its damage primarily through indirect mechanisms involving free radical production. UVB is the primary driver of sunburn. It is energetic enough at the wavelengths that reach the Earth's surface to cause direct damage to DNA molecules in skin cells. When UVB radiation penetrates the outer layers of skin and reaches cells, it is absorbed by DNA. The energy from that absorption causes adjacent thymine bases on the DNA strand to bond together in abnormal configurations called thymine dimers. These dimers distort the DNA helix structure and, if not repaired, cause errors in DNA replication, which is why UV exposure is a primary driver of skin cancer. The cell's DNA repair systems work continuously to identify and correct thymine dimers, but when UV exposure is intense and prolonged, damage accumulates faster than repair can keep pace. The redness, pain, heat, and swelling of sunburn are not caused by the UV radiation directly. They are caused by the inflammatory response that follows DNA damage. Damaged skin cells release inflammatory signaling molecules that dilate blood vessels, increase blood flow to the affected area, and recruit immune cells to begin the repair and cleanup process. The heat is vasodilation. The pain is the activation of pain receptors by inflammatory mediators. The peeling that follows a few days later is the skin shedding the layers of damaged cells whose DNA was too compromised to repair. Sunburn is, at root, a visible manifestation of the fact that significant DNA damage has occurred in the outer layers of your skin, and your body is mounting an inflammatory response to deal with it. This happens to humans with notable ease. It does not happen to most other animals under ordinary circumstances. The reason why is the story of what protects skin from UV radiation and how different lineages solved the protection problem. Fur is the answer that applies to the majority of mammalian species. And its effectiveness as UV protection is so comprehensive that it essentially renders sunburn a non-issue for furry animals even under intense sun exposure. Dense fur functions as a physical barrier to UV radiation. The keratin proteins in hair shafts absorb UV radiation efficiently, preventing it from penetrating to the skin surface below. Studies measuring UV transmission through animal fur consistently find that the radiation reaching the skin beneath a full coat of dense fur is dramatically reduced, in many cases to essentially negligible levels. A lion, a dog, a sheep, a horse, their fur is not decorative. It is, among other things, a highly effective UV blocking layer covering the vast majority of their body surface. Most mammals with dense fur coats effectively never expose their skin to direct UV radiation under natural conditions. The fur handles it. The skin underneath can be, and in many species is, quite pale and UV sensitive, because there has been no evolutionary pressure to develop UV protection at the skin level when the fur is providing comprehensive coverage above it. Humans lost this protection, and examining why requires understanding one of the most consequential evolutionary transitions in hominin history: the loss of body hair that accompanied the transition to life on the open African savanna. The evolutionary timeline of human hair loss is not perfectly resolved, but the genetic and fossil evidence points toward a gradual reduction in body hair beginning somewhere between 1.5 and 3 million years ago, broadly coinciding with the emergence of Homo erectus and the transition from forest-dependent to open savanna-adapted hominin lifestyles. The driving force behind hair loss in human ancestors was almost certainly thermoregulation, the management of body temperature during sustained physical activity in hot, open environments. The open African savanna is a thermally brutal environment. Air temperatures are high. Solar radiation is intense. The vegetation that would otherwise provide shade is minimal compared to forest environments. And the hunting strategy that early Homo was developing, persistence hunting, the practice of tracking prey over long distances until heat exhaustion forces them to stop, required sustained aerobic activity in exactly these conditions. Mammals manage heat through panting, through behavioral thermoregulation, and in some cases through sweating. Humans sweat at a rate and across a body surface area that is unmatched in the mammalian world. Human eccrine sweat glands, the kind that produce the watery sweat that enables evaporative cooling, are distributed across the entire body surface in densities far exceeding those of other primates. A human exercising hard and hot conditions can produce several liters of sweat per hour, enabling continuous evaporative cooling that keeps core body temperature stable during sustained activity. But sweat-based evaporative cooling is only effective when the sweat can actually evaporate from the skin surface. Dense fur traps a layer of humid air against the skin, impeding evaporation. A body covered in thick fur cannot cool itself efficiently through sweating because the fur prevents the air circulation that drives evaporation. Reducing body hair removed the impediment to evaporative cooling, allowing human ancestors to exploit sweat-based thermoregulation with the efficiency that persistence hunting required. The trade was this: thermoregulatory efficiency in exchange for UV protection. Losing the fur coat let early humans hunt effectively in conditions that exhausted prey animals. It also exposed their skin, for the first time in the history of the hominin lineage, to direct UV radiation without the buffering layer of hair that had previously protected it. Evolution does not make trades blindly. It responds to selection pressure, and the sudden, comprehensive UV exposure of newly bare skin created exactly the selection pressure that drove the rapid evolution of melanin-based UV protection in the exposed African hominin. Melanin is the pigment that gives human skin its color, and understanding its UV protective function explains both the evolution of dark skin in tropical populations and, indirectly, why fair-skinned people burn so readily. Melanin is produced by cells called melanocytes, which are distributed throughout the basal layer of the epidermis. Every human being, regardless of apparent skin color, has approximately the same number of melanocytes. What differs between individuals and populations is not the number of melanocytes, but their activity. How much melanin they produce, and what kind. There are two primary forms of melanin in human skin. Eumelanin, which is dark brown to black in color, provides efficient UV absorption and photoprotection. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Pheomelanin, which is red to yellow in color, provides substantially less UV protection, and under some conditions can actually contribute to UV-induced damage through the generation of reactive oxygen species. Darker skin has higher eumelanin production. Lighter skin has lower eumelanin production, and in some cases higher pheomelanin relative to eumelanin. Melanin protects skin cells from UV damage through two mechanisms. First, melanocytes transfer melanin granules into surrounding keratinocytes, the primary cells of the outer skin layer, where the melanin forms a cap over the cell nucleus, physically shielding the DNA from UV radiation, like a microscopic umbrella positioned between the radiation source and the genetic material. Second, melanin absorbs UV photons and dissipates their energy as heat rather than allowing that energy to be absorbed by DNA, converting a DNA-damaging photon into harmless thermal energy before it can cause a thymine dimer. In populations native to equatorial Africa, the evolutionary context in which human skin lost its fur cover, eumelanin production is high, providing robust UV protection that prevents sunburn under ordinary conditions of tropical sun exposure. The evolutionary logic is direct and powerful. On the open African savanna without fur, UV exposure is intense and continuous. DNA damage from UV radiation causes skin cancer reduces reproductive fitness, and individuals with higher eumelanin production are better protected, survive longer, and reproduce more successfully. The problem, from the perspective of that family at the beach, is what happened next. Modern humans migrated out of Africa beginning roughly 60,000 to 70,000 years ago, moving into environments with dramatically lower UV radiation than the equatorial African context in which dark, highly eumelanin-rich skin evolved. At higher latitudes, UV radiation intensity decreases significantly. Seasonal variation in UV exposure is extreme. High UV in summer, very low or negligible UV in winter. At latitudes above roughly 50 degrees north or south, winter UV levels are insufficient for significant vitamin D synthesis in the skin for months at a time. Vitamin D, the nutrient synthesized in skin through UVB-dependent reactions, is critical for calcium metabolism, immune function, and a range of other physiological processes. The irony of the UV story is that the same UV radiation that causes DNA damage and drives sunburn is also the primary mechanism through which humans synthesize adequate vitamin D. Without sufficient UV exposure, vitamin D synthesis drops, and deficiency produces serious health consequences including rickets, immune compromise, and increased risk of various diseases. In equatorial Africa, UV radiation is so intense that even heavily melanin-pigmented skin receives adequate UVB for vitamin D synthesis throughout the year. But at high latitudes, the reduced UV levels mean that high melanin content, which absorbs UVB before it can drive vitamin D synthesis, just as it absorbs UVB before it can cause DNA damage, becomes a liability rather than an advantage. High eumelanin production in low UV environments produces vitamin D deficiency. The selection pressure reversed. At high latitudes, lighter skin, lower eumelanin production allowing more UVB to penetrate for vitamin D synthesis during the limited sun exposure available was advantageous. Populations that remained in high-latitude environments for many generations underwent selection for reduced melanin production, producing the lighter skin tones of Northern European and Northeastern Asian populations. That lighter skin produced more vitamin D in low UV conditions. It also, when those populations or their descendants moved to high UV environments, burned dramatically more readily than the ancestral African skin from which it had depopulated its melanin. The family at the beach, in other words, is experiencing the consequences of their ancestors' successful adaptation to low UV environments. The adaptation that helped their distant forebears thrive in northern latitudes is spectacularly mismatched with a beach afternoon in direct subtropical sun. Animals other than mammals solve the UV problem through mechanisms that are worth examining, because they reveal the range of solutions evolution has produced to the same fundamental challenge. Birds present a fascinating case because, like humans, they have relatively thin skin with limited structural protection. Unlike humans, most birds have feathers covering the overwhelming majority of their body surface. Feathers that, like mammalian fur, provide physical UV blocking above the skin level. The exposed skin of birds, their legs, feet, and facial areas, is often heavily pigmented, or in some species protected through other mechanisms. Some bird species have evolved melanin-rich skin on their exposed areas that provides UV protection comparable to heavily pigmented human skin. Others have developed structural color in their feathers that is partly UV reflective. Certain species of birds can see into the UV range. Their eyes detect wavelengths invisible to humans, and use UV reflective feather patterns in mate choice, a capability that has nothing to do with UV protection but demonstrates how thoroughly UV radiation features in avian biology. The melanocortin receptor system that controls melanin production in mammals is present in birds in a modified form, and birds show similar patterns of melanin variation linked to UV environment. Species living in high UV environments tend toward darker coloration compared to close relatives in lower UV environments, following the same basic evolutionary logic as human skin color variation. Reptiles offer yet another approach. Many reptiles actively seek UV exposure as a behavioral strategy. Basking is partly thermoregulatory but also serves to enable vitamin D synthesis, since reptiles share the UVB-dependent vitamin D pathway with mammals and birds. Reptile scales contain melanin and also provide physical UV blocking through their overlapping dense structure. The spectacularly UV-exposed iguana on its equatorial rock is protected by a combination of heavy melanin pigmentation and the physical barrier of its scaled integument. Hippopotamuses deserve their own section because they represent one of the most extraordinary solutions to UV protection in the entire animal kingdom. And it is bizarre enough to be genuinely memorable. Hippopotamuses spend their days in water, which provides UV protection through shading and the filtering effect of water. They emerge in the evening and night to graze on land. But they also spend time at the water's surface, partially exposed to direct sunlight during daylight hours, and they have essentially no hair and notably thin, sensitive skin that lacks the melanin density of most sun-exposed mammals. Hippopotamuses produce their own sunscreen. This is not a metaphor. Their skin produces a reddish secretion that for decades was colloquially described as blood sweat, which it absolutely is not, despite being both reddish and secreted by the skin. The secretion contains two pigmented compounds, hipposudoric acid, which is red, and norihipposudoric acid, which is orange, that absorb UV radiation across both UVA and UVB ranges. The same compounds have demonstrated antimicrobial properties, suggesting the secretion serves multiple protective functions simultaneously. The hippo's skin secretion is, functionally, a biological sunscreen produced internally and excreted through the skin, solving the UV problem through biochemical synthesis rather than through melanin pigmentation or physical covering. This solution is unique among large mammals as far as current research has established and represents yet another evolutionary pathway to the same outcome, preventing UV-induced skin damage in an animal that experiences significant sun exposure. The hippo did not develop this capability by choosing to. It evolved in a population where individuals with more effective secretion survived longer and reproduced more successfully, eventually producing the remarkable biochemical sunscreen that modern hippos deploy without a single conscious thought about SPF ratings. Elephants present another interesting case because, like humans, they are large, relatively hairless mammals that live in high UV tropical environments and cannot rely on fur for UV protection. Elephants have highly melanin pigmented, Skin that provides significant UV protection, but they also engage in behavioral UV protection with striking consistency. Dust bathing, mud wallowing, and seeking shade during peak UV hours. Young elephants in particular, whose skin is lighter than that of adults, are observed to seek shade and mud more consistently than older animals. Elephant skin also has a distinctive structural feature: deep wrinkles and folds that trap moisture and mud, helping maintain the external coating that provides both UV protection and thermoregulatory benefit. The wrinkled texture is not purely incidental to elephant aging. It is a functional feature that maintains the behavioral UV protection strategy more effectively than smooth skin would. This combination of melanin pigmentation and behavioral photoprotection is actually quite similar to the solution that dark-skinned humans evolved: high melanin production combined with behavioral responses to extreme UV conditions. The parallel is not coincidental. Both elephants and tropical humans are large, relatively hairless, high UV environment mammals who converged on overlapping solutions to the same UV challenge through independent evolutionary pathways. Marine mammals, seals, sea lions, walruses, dolphins, whales, represent perhaps the most extreme case of UV exposure among mammals, since they combine the hair reduction associated with aquatic streamlining with regular time spent hauled out on sun-blasted rocks or at the ocean surface. Cetaceans, whales, and dolphins live entirely in water, which provides substantial UV filtering, and have highly melanin pigmented skin on their dorsal surfaces that provides additional protection. Studies of wild cetaceans have found evidence of UV-induced DNA damage and inflammatory responses in light-colored species like blue whales and fin whales, suggesting that UV exposure is a genuine biological challenge even for these ocean-dwelling animals. Interestingly, blue whales showed higher rates of UV-related skin changes in lower latitude, higher UV ocean regions, a distribution consistent with UV being the causative agent. Pinnipeds, seals, and sea lions present a more dramatically exposed case. Harbor seals hauled out on rocks spend hours in direct sunlight regularly. They have relatively sparse hair providing limited UV protection. Research has documented that pinnipeds produce antioxidant compounds in their skin and have DNA repair mechanisms operating under the consistent UV load they experience. They also show behavioral photoprotection, changing positions, slipping into water during peak UV hours, and orienting their bodies to minimize direct sun exposure to the most sensitive skin regions. Even animals that appear totally unbothered by sun exposure are, at the biological level, actively managing the UV challenge through pigmentation, biochemistry, DNA repair, or behavior. The difference between them and a sunburning human is not that UV radiation is harmless to them. It is that their biological toolkit for managing UV exposure is more comprehensive than what evolution provided to lightly pigmented humans in high UV environments. The skin cancer statistics make the evolutionary stakes of UV protection viscerally clear. Skin cancer is the most diagnosed cancer in the United States, and numerous other countries with significant populations of light-skinned people living in substantial UV environments. Melanoma, the most dangerous form of skin cancer, kills tens of thousands of people annually worldwide. The incidence of skin cancer is dramatically higher in populations with lower melanin production living in high UV regions than in populations with higher melanin production in equivalent UV environments. This is evolution's prediction playing out in modern public health data. The UV protection afforded by high eumelanin production is not cosmetic. It is functional, measurable, and consequential for survival and reproductive fitness. The populations that evolved in high UV environments under natural selection pressure are the ones whose melanin production most effectively prevents the DNA damage that leads to skin cancer. The populations that evolved in low UV environments, whose lighter skin was adaptive in those contexts, face elevated skin cancer risk when living in or visiting high UV environments because their melanin levels were calibrated to a different UV reality. The modern mismatch: fair-skinned people at beaches in UV environments their skin was not optimized for, is exactly the kind of evolutionary mismatch that evolutionary medicine examines as a source of disease. The family at the beach is not doing anything unusual. They are experiencing the predictable consequence of skin that was optimized for Norwegian winters encountering Floridian July afternoons. The sunscreen that family should have reapplied every 2 hours is, in chemical terms, attempting to replicate externally what evolution provided internally to populations with high melanin production. Modern sunscreens use organic UV-absorbing compounds and physical UV-blocking particles, zinc oxide, titanium dioxide, that function through mechanisms analogous to melanin's UV absorption. They are applied externally, wash off in water, degrade under UV exposure, and require reapplication. Melanin is produced internally, is present in the skin tissue itself, does not wash off, and is renewed continuously as skin cells turn over. The biological solution is considerably more elegant than the commercial one, but the commercial one is what evolution did not provide to populations that spent enough generations at northern latitudes to lose the melanin density that tropical UV environments demand. Here is where this entire exploration, from the family on the beach to hippopotamus sunscreen biochemistry to the evolutionary history of human hair loss, arrives at something genuinely worth holding on to. Humans are not uniquely fragile in the face of ultraviolet radiation. Humans are uniquely naked mammals who live across the full UV range of the planet's latitudes, and who carry, in their populations, a range of melanin levels that reflect adaptation to radically different UV environments. Dark skin in tropical populations is not cosmetically different from light skin in northern populations. It is functionally different, calibrated to different UV environments by selection pressures operating across thousands of generations. The pelican on the post is not tougher than the burning family. It is protected by feathers that cover its skin surface comprehensively in ways that human ancestors traded away for the ability to outrun prey on the open savanna 2 million years ago. The hippo produced a biochemical sunscreen through millions of years of selection in sun-exposed, hairless conditions. The elephant combines melanin and mud because one solution is not always enough. Every animal that handles UV radiation without burning has a story. A set of evolutionary solutions developed over generations of selection pressure in the UV environments they inhabit. Those solutions range from the straightforward to the biochemically extraordinary. Humans have melanin. Humans who evolved in high UV environments have a lot of it and are substantially protected. Humans who evolved in low UV environments have less of it and are substantially less protected when UV conditions exceed what their skin was calibrated for. The solution the modern world has produced, sunscreen, clothing, shade, behavioral adaptation during peak UV hours, is not fundamentally different from what evolution produces when it has time to work. It is just faster. It is deliberate. It is the human capacity for cultural and technological response to biological challenges doing what it does, solving in a generation what evolution takes thousands of generations to address. Reapply every 2 hours. Do not forget the backs of your knees. The pelican on the post will judge you either way, but at least you will be able to sleep tonight.